Hey guys, Mr. Newman here, and today we're going to work on limits, both graphical and analytical. All right. So first of all, the limit of a function is a number, in other words, the y value that the function produces as you approach an x value from either side. And from either side, it really needs to approach from both sides for the limit to exist. Okay. So let's talk about some notation. First of all, that's how you write a limit. The way you say it is the limit as x approaches c of f of x. You notice this little plus right there, and the next time I write that, that's how you denote that the limit is coming in from the right side. So let me draw a little picture here. And you copy this down for me. From the right side is literally, if you're looking at the graph, from the right side of the graph. In other words, the positive side of the function. So you see my little arrow I have there? That's coming from the right side. That's coming from the positive side. So that little plus up there, it looks like an exponent. It actually means the limit coming from the right side. In this case, that limit from the right side would be -1, because as you move from the right side, from the positive side, and get closer and closer to that center there, you're getting closer and closer to -1. On the other hand, that if there's a negative there, a minus, that's the limit from the left side. So if you picture on that picture there, coming from the left side or the negative side, you're getting closer and closer to the value 1. Okay? So in order for a limit to exist, both the right side and the left side must be equal. So then this drawing I have here, this is an example of case number 1, where the limit from the right side, which is right here, is not the same as the limit from the left side, right here. In that case, the limit does not exist. The second case where the limit doesn't exist is if f of x increases or decreases without bound. Now, those, you see these vertical asymptotes right here, those are increasing without bound. So even though the limit from the left is infinity and the limit from the right is infinity, in calculus we say that this limit does not exist. So that's the second case. In the third case, that's where the function oscillates between two fixed points. Oscillates is a word that means goes back and forth between. So, an example of this would be the cosine function. Notice it oscillates, or it goes back and forth between -1 and 1. So there is no limit. As you keep going out to the right, to infinity, there's no limit for this function. This can also oscillate back and forth like this, converging to a point, and that's a really cool function we'll look at later. But if it doesn't go to one single point, then it does not, the limit does not exist. Let's look at this graphically, okay? First of all, in this first one, I want you to see here the limit as x approaches -5 from the negative side, or from the left. What we're going to do is here, we're going to look at this graph, we're going to determine the limit purely from the graph. Now remember, the limit is the y value as the x value approaches something. So when I say a number that's the value of the limit, I'm looking at the y value, or the y-axis of that point. This first one, as x approaches -5, I find -5 on the x, and we're approaching it from the left. So I'm going to draw a line. You see that my green arrow, if I'm walking along the function along the left side, I'm getting closer and closer to the y value of 3 as I get really close to the x value of -5. That means the limit from the left is 3. For the next one, notice that minus up there changed to a plus. This is the limit as x approaches -5 from the right. For this one, we're coming from the right side, or the positive side of -5. And as I get closer and closer to the x value of -5, I get closer and closer to the y value of 3 as well. Because the left and the right limits are equal, we say that the limit exists. So the limit as x approaches -5 of f of x is 3. I want you to notice something, however. The function at -5 does not equal 3. You see the function at -5, there is a hole there, or rather an open circle at the point -5, 3. The function is actually filled in down there at -5, 1. So the y value at -5 is 1. This is a case where the limit exists, but the limit does not equal the value of the function at that point, and that can happen. That's fine. The limit is independent of what is actually happening at that point. The limit only tells us what is happening at the function as you get really, really close to that x value. Let's look at the next one. For -3, as you approach -3 from the left, it is going up without bound. It's approaching infinity. So we can say the limit from the left is infinity. On the right, the same thing is happening. From the positive or the right side, the limit as x approaches -3 from the right of f of x is infinity. Because these limits are increasing without bound, because they do not approach an actual value, we say that this limit does not exist. Now you are allowed to abbreviate does not exist with DNE. So when you write that, we assume that means does not exist. Let's continue with the next one. When as the function's approaching -2 from the left, I'm going to draw a little arrow there. Remember that the graph of the function is actually a bunch of points. So we are getting closer and closer to this point right here. Now I just sketched that in. You don't need to sketch that in because you know that that's what the curve means. So as we're getting closer and closer to the x value of -2, what are we getting closer and closer to on the y? Well, 3. That's because I'm looking right here. That's this 3 right there. From the right or positive side, the same thing is happening. We're getting closer and closer to the y value of 3. Because the limit from the left and the limit from the right are both equal and they both exist, that means the limit as x approaches -2 of f of x is 3. For the one thing I want to point out here is that in this case, the function, the value of f of -2 is equal to the limit, and that frequently happens. For the last one here, let's look at as x approaches 3 from the left. Notice that we are getting closer and closer to the y value of 1. But as x approaches 3 from the right, or the positive side, we're getting closer and closer to the value of -1. Because these two limits are not equal, we say the limit from the left and the right are not the same or not equal, this limit does not exist. That's how you find limits graphically. Let's move on to finding limits analytically. And when you see the word analytically in this class, that in my mind, I'm thinking algebraically. There's often some kind of algebra you're doing to evaluate it. Now, a lot of these rules are fairly commonsensical. Let's go through some of them. First one says, if you have a constant function, the limit as you approach anything is that value, that constant. That makes sense because you're approaching it, it's the same as the constant function. It's always going to be that value, that b, whatever b is. The other two and three here, are simply saying if you have a linear or exponential function, you just substitute the value in. You just plug in whatever number you're getting closer and closer to. You plug that number in, and you can evaluate it at that point by plugging the number in or substituting the value in. Down here, these other properties are other ones that I would argue or just say are what are common sense in the sense that the limits do what you think the limits are going to do. Okay? For example, the limits work as you would guess they would work if you were just guessing. For this first one, the scalar multiple just says if you multiply a function by a number, then the limit is going to be equal to the same thing multiplied by that number. Okay? In the second one, it just says if you add two functions together and take the limit of that, that's the same as finding the limit of each one and adding them together or subtracting them. Same with the product, same with the quotient. You have to make sure the denominator is not 0 in that case, and same with the power. In other words, if you can find a limit, if you do something to that function originally, the limit of that new function is just going to be whatever you did to that original function. Okay? This composition function down here is going to be helpful because what it says is when you're finding out or evaluating a limit of a composition of functions, you can find the limit of the inside function first and then evaluate that function. Okay? So you find the inside limit first when you're working through those. That's the way to solve those, much as you would evaluate a function. All right. let's do some of these. First thing I want you to do is, if you don't have cancellation, if you have cancellation there, if you've ever had me before for a class, I don't like the word cancellation or canceling, because in my mind, two things cancel out, 0 is left over, nothing's left over. But in this case, we're specifically talking about dividing out, and when you divide a number out, 5 divided by 5, for example, you get 1. So I like the word dividing out, but let's go over these 4 techniques to analytically or algebraically find the limit. First of all, direct substitution. As long as the denominator is not 0, you can plug the limit straight in. We'll show you that with number 1 and some of the other ones later. And it's very, I just want to say something else here. It's very often that students forget this when we're getting to more complex limits. Always remember that if you are able to plug a number in, do so with the limit. Okay. For dividing out, this is a technique. You simply often will factor and then you divide out. That way you are able to use direct substitution. Rationalization is one where you multiply the numerator and denominator by the conjugate, and just remember that conjugate means you change the ending, and so I'll remind you guys of that when we get to that kind of problem. And for trig identities, one way to do this is to change everything to sine and cosine, and then you divide things out. And often, or frequently, this will give you the limit, and you will be able to use direct substitution again. So actually, all of these, 2, 3, and 4, are ways for you to get back to doing number 1, using direct substitution, plugging the value of the limit, directly into the function. So let's start doing some of these problems here. Let's look at the first one here. The limit as x approaches 2 of x plus 4. Because you are allowed to plug in 2, we're going to directly substitute that in, and you get 2 plus 4, or 6. There are no problems when you plug in 2, so we can just plug it straight in. And we're done. For number 2, if we tried to plug in 2 here, if you look at the denominator, we would get 0 in the denominator. So we can't use direct substitution. We need to do something to that. And since it's a rational function, there's a very good chance that something will divide out when we factor it. Now I'm going to pause right here, and I need to talk about this right here. I am doing the problem. I have not yet substituted in my value, so I need to write the limit as x approaches 2. I know that some of us are lazy because I was one of those lazy students back when I was in high school, but this is a habit you need to develop because the AP test does not care a whole lot about getting the right answer. It cares much more about the process of that answer and using correct notation to get to that answer. You can do a problem where you get the right answer and only earn 1 out of the 4 points. You need to learn to write the correct work out, and you need to learn how to show your work, because in this situation, if you are finding a limit and you do not write the limit, you will actually lose points simply by not writing that part that I put there in red. So I'm going to be frequently reminding you to write the limit up here up front early on so it becomes a habit, because if you are not writing it now and don't make it a habit, you will not remember it on a high stakes test like the AP test. So, having said that, make sure you are writing the limit as x approaches 2. Now notice we factor the numerator and denominator. X minus 2 divides out on top and bottom. So we get, again, write the limit as x approaches 2, again, x minus 1 over x plus 3. Now, there's no problem with substituting a 2 in for x because the denominator will not be 0. So we substitute a 2 in for x. We don't need to write the limit anymore because we substituted in. It's no longer a limit, it's actually a value. And we got 1/5. Moving on to number 3. Again, write the limit as x approaches 0 for each step prior to substituting it in. Tangent is sine over cosine. So I'm going to write down sine over cosine instead. Now we have a fraction divided by a fraction. If you remember your fraction rules, when you have a fraction over a fraction or a fraction over a value, dividing is the same as multiplying by the reciprocal. Write your limit. I'm going to multiply by the reciprocal. Now the reciprocal of sine of x is 1 over sine of x. Now I can see much more clearly the signs can divide out. So we get 1 over cosine of x. At this point, plugging in 0 or substituting in 0 is not a problem because cosine of 0, if you think about the graph, cosine of 0 is 1. Up here, however, sine of 0 is 0, so we could not have plugged it in the initial. And I forgot to mention, we should always check that because if you can, you save yourself a lot of work. And one of the strategies or one of the goals for this class is to get you answering these questions quickly because the AP test is a timed test, and that is one of the things that the AP test measures, how quickly you can do these problems. So we get 1 over 1, which is 1. Moving on to number 4, again, write the limit as x approaches 2. I notice that I cannot substitute 2 in because of the denominator would be a 0. So I factor difference of squares in the numerator. X minus 2 can now be divided out. Now I can substitute a 2 in, and we get 4. For number 5, be very careful. Make sure you write the limit. You might say, hey, I can factor that numerator, but wait. Can we substitute it in? Yes, you can substitute it in. So you don't need to write this limit. Let me erase it. You don't need to write the limit if you substitute it in. So this is one of those cases. This happens a lot in calculus. You overlook the first simple step because you are doing more complicated stuff. Make sure you go back to the steps, and as long as you are checking to see if you can plug it in, you can usually solve these a lot faster. So looking here, that's going to be 0 because the numerator is 0. 0 divided by 6 is 0. Number 6, this is the first example of rationalizing the problem. Notice we are not actually rationalizing the denominator. That is actually technically a simplified function right here. We're actually rationalizing the numerator. And you're going to see, notice how if we plug in 0 here, we get 0 in the denominator. Using this technique, we are going to be able to substitute in 0, and it will not give a 0 in the denominator. So let's first talk about what is a conjugate. Well, a conjugate is where you change the ending. And in this case, the ending is that minus 1. Okay? If those were switched around, if we had the negative 1 up front and had plus the square root of x plus 1, then we would simply make the radical, the square root, we would make that negative instead of positive. That will also work. In this case, I'm going to write it out like this because it's much easier, in my opinion, to see. Notice we actually have in the numerator here a difference of squares when we write this, and that's your goal when writing the conjugate. So notice if it was negative 1, we're just going to change it to positive 1. So we have our difference of squares. You need to know the difference of squares formula, so you don't need to multiply all this out. Though you could do with a Punnett square maybe the first time, but after that, notice because of that plus, we're now going to simply multiply those out. Remember, a difference of squares is the first one squared minus the second one squared. Very much like number 4 back here. Remember how you had x squared minus 4 and you recognize that as difference of squares? It's just we're going the other direction. The square root of x plus 1 squared, that's just x plus 1. The square root, 1 squared is just 1. So when you notice, you skip a lot of unnecessary work being written down when you have your difference of squares memorized. The denominator looks a little messy, but it'll clean up soon. Don't worry. In the numerator, we're going to combine the positive 1, negative 1. We get x in the numerator. Now the x's divide out, and we get 1. Notice I didn't say cancel out because I might accidentally write a 0 if I were canceling out. They are dividing out there. We get 1 over the square root of x plus 1, plus 1. And at this point, I can now substitute in the 0. So I'm going to do that. I get the square root of 1 is 1. 1 plus 1 is 2, so we get 1/2. Moving on to number 7. Number 7 is really connected to part A, B, C, and D. And this is the part where I explained the limits are going to do what you think they're going to do. If you have an 8 multiplied on the inside of the limit here, you can actually pull that 8 out to the front. And that means that's the same as 8 times this limit. Now notice this part right here. Notice that's the same as what they gave us. So that whole thing right there is just 3. So I'm just going to substitute that in and say that's 3 because it is equal to 3. So we get 8 times 3 or 24 for this first one. Part B, if you have a limit and you have them added together, that's the same. The limit of the sums is the same as the sum of the limits. In other words, we can just rewrite this as 3 plus negative 4 and get negative 1. Part C, the limit of products is the same as the product of limits. So we can write this as the limit as x approaches 2 of f of x times the limit as x approaches 2 of g of x. I don't know if you've noticed, all of these have these brackets here. The brackets are just another way of writing parentheses. Remember that brackets and parentheses are interchangeable, so don't be confused by that. We get 3 times negative 4, which is negative 12. And lastly, the limit as x approaches 2 of f of x over g of x, we can write the limit of the quotient as the quotient of the limits. So we get 3 over negative 4. In other words, all of these, if you were just guessing, I'm guessing you guys would get these correct without even having those properties, and those are nice. All right, number 8. For number 8 here, we need to get a common denominator. So, in order to get that common denominator, let me rewrite this. First, I'm going to write down, remember, this is going to be one of those trials where you're writing a lot of stuff. You need to practice writing the limit as x approaches 0. That way you do that on the final test. So, I'm going to write all this out, and we need a common denominator just in the numerator. So I'm going to multiply the top left fraction by 4 over 4, and the top right by 4 plus x over 4 plus x. And then I'm going to multiply that out. Now, I would say, if you can get to the point where you just need to write that step out, and you don't have to write that step that I have there in green, great, go for it, okay? Make sure you're doing it correctly. If you're messing up over and over, start showing more of your work, okay? If you're getting it and feel that you can leave steps out, that is a step that you can leave out, all right? This is one of those things where if you can write that to that step, the AP graders understand that you know what you're doing, all right? Now, for this, we need to do 4 minus 4. You notice I got a negative x in the numerator because this minus here needs to be distributed to both of them. That is a common mistake. Now that I have a fraction over a fraction, I can use my technique of division is the same as multiplying by the reciprocal. Well, the reciprocal of x is 1 over x. Now I can divide those x's out, and I get negative 1 in the numerator and 4 times 4 plus x in the denominator. Notice I kept writing the limit as x approaches 0 because I have not yet substituted in the 0. At this point, I'm going to do that because 4 plus 0 is 4. 4 times 4 is 16, so we get negative 1/16. All right, thanks for hanging here. This has been a long video, but for the last one, we're going to do a piecewise function, and this works a little differently. It's asking for the limit as x approaches 3. Now, notice because of that, let me go back here just a bit. Whoops. Notice that because it asks for x approaches 3, and 3 is, I call these on the edge, but it's where the function changes from x to x minus 4, right? That's the way piecewise functions work. I'm going to need to test this from the left and from the right just to make sure that those are the same, because if they're not equal, this limit does not exist. So let's write that out. So the function from the right, or from the positive side, and the function from the left, or the negative side. Next thing I need to do is I need to figure out, well, which of these functions is the left and the right side. This first part of the piecewise function says x is less than 3. That means that that's going to be the left side of the limit. Often I like to draw these out, but if you can do this without drawing this out, that will save you some time here. So picture with me, x is less than 3. That's going to be the left side of our limit. Right here, it says x is between 3 and 4. That means that's the part that is greater than 3. So this is the part of the function which is on the right side of our limit being the x value of 3. Now that I know that those functions x and x minus 4 are the two functions I'm going to use. Let me just make sure I match them up correctly. Let's see, I'll do the blue one first. So because that's the right side of the limit, I can use x minus 4 as my function on the right side of 3, because it is the function that is just a little bit to the right of 3. Now that I have that, I can just substitute in the 3 because there's no problem with substituting a 3 in here. Now notice, this is a 3, not a 3, positive 3, or a 3 with some other kind of special plus up there. It is positive 3, but it's just 3 that I'm going to substitute in. So I substitute in the 3, and I get 7. That's the value that the piecewise function is approaching as you approach 3 from the right. As for the left, I'm just going to substitute in x because that's the function right here for when the x values are less than 3. In other words, the left side of our limit. Now that means I can just substitute the 3 in there for the x. So I do that. Well, what do we have here? We have from the right it's 7, from the left it's 3. That means this limit does not exist because, and you want to say something like this, this is actually the most concise way to write it, is using the math symbols. Because the limit as x approaches 3 from the left is not the same as the limit as x approaches 3 from the right of this function. Okay? Thank you for watching.